Hello, good people. Welcome to video one of topic 1.5. If you're paying attention, we skipped 1.4. We'll come back to that. We'll discuss what happened there. But this topic is going to make the transition from looking at limits using graphs, in which it's somewhat easier um, investigating whether or not the limit exists and where the limit is, to looking at equations. And so the experiences that we've been having with graphs, we're going to continue to have the same experiences, except we're going to be using equation symbols instead of pictures, graphs. So the most important concept, the most important idea for limits that you need to remember is this. So I'm going to read this statement right here. And if you'll follow along, remember what the statement parts are saying. The limit of f of x as x approaches c will exist if and only if the limit of f of x as x approaches c from the left side is the same as the limit of f of x as x approaches c from the right side. If you watch the other videos, I refer to what I call the finger test, right? If you put your finger on the graph and you get closer and closer to an x value, are my fingers going to the same place? Because that means that the limit from the left and the limit from the right are equal because they're going towards the same value. Well, the limit is only going to, what this statement says is the only way for a limit to exist is if the left and the right side approach the same thing. So let's write down what this says. This means a limit, and in parentheses, I'll put a full limit from both sides. Let's just write a full limit exists only if the left and right sided limits are the same. So if you take the limit from the left and you get an answer, and you take the limit from the right and you get an answer, and the answer is the same, well, then the full limit exists from both sides. So it's easy to check the left side and the right side when we're given a graph, but when we're working equations, it gets a little iffy. If we know that we're working with a continuous function, continuous, what does continuous mean? It means that there is no break, there's no hole, there's no asymptote to it. It's nice and smooth, right? Everything's connected. Continuous means connected. So if I have a continuous function, we really don't need to worry about the left and right side limits because we know, because everything's connected, that from both sides of the same x value, we're going to get the same answer, the same limit. But when we're dealing with piecewise functions, that's when things can get a little bit hairy. And that's what 1.5 is telling us to do. So one of the types of functions that you'll see throughout the exam, APA calculus exam, is can you read a piecewise function? Can you find the limit of a piecewise function as x approaches a specific value or as x approaches infinity? And that's what we're going to practice here in video one. For video one, I'd like to do all the F-related limits. Okay, so that means we're only doing these four in this video. And we're looking specifically at this function. It says the functions f of x, g of x, and h of x are piecewise defined, and they're given below. Use the functions to evaluate the following if it's possible. It might not be possible. So the first one I'll do in green. We're going to take the limit of f of x as x approaches 0 from the left. From the left. So what kind of values are on the left side of 0? Are those values bigger than 0, or are those values smaller than 0? So if I'm approaching 0 from the left, think of the number line. If I'm coming from the left side, all of those x values are less than 0. So therefore, I'm using the top piece because that function defines the side of the graph that's to the left of 0, x's that are less than 0. So as I'm coming from the left, x's are less than 0, that's the formula I'm going to use. So what does that look like? Well, 2x minus 3, if you remember your algebra, is just a line, right? So what we can do is we can use what we call direct substitution to see what would be the y value. Because if we can figure out what the y value is, and if we know that that function graph is a continuous function, then whatever the y value is, that's what the limit's going to be. I hope that in the practice that we've done, you've noticed that limits don't exist when there are issues with the graph, right? When the graph is like this, or when the graph is like this. Whenever there are issues with the graph, there's a possibility that the limit doesn't exist. However, if the graph is continuous and everything's connected, then we know that the limit will exist. And the limit is the y value. So what we can do is we can say, I'm going to take the formula and I'm going to plug in my x value. And when I do that, I get my answer. So we call this direct substitution. If we're given formulas, we can directly substitute the x value if we know that that function is continuous. Continuous meaning there aren't any holes, there aren't any breaks, there aren't any jumps, there aren't any vertical asymptotes. Everything's nice with that part of the graph. Okay, so using the same f function, we're going to find the limit of f of x as x approaches 0 from the right. So if we're coming from the right, that means all those x values are bigger than 0. So we're going to use this. And we ask ourselves, do we know what that looks like? From Algebra 1, Algebra 2, Pre-Cal, do we know what x squared plus e to the x looks like? Maybe, maybe not. But is each of those pieces continuous? Is x squared continuous? Sure, it's just a parabola. Is e to the x continuous? Sure, it's just an exponential. So when I put them together, they should be continuous. So again, I'm going to take my formula and I'm going to substitute directly in the value that I'm approaching. I'm approaching 0, and even though I'm just approaching 0 from the right side, from only one direction, I can substitute that number, and if I get an answer, well, then that's the limit. And I know that because my function is continuous. By the way, e to the 0, any number to the 0 power is 1, and so therefore my final answer is 1. Direct substitution says if we can figure out which piece of a piecewise function we're dealing with, then we can just substitute in the number and we're going to get the value of the limit. All right, we get to letter C. Find the limit of f of x as x approaches 0. Well, that's a full limit, not left only, not right only, but from both sides. So the question is, if I go back, if I look at this part, and if I go back, do the left and the right agree? Because that's what we've set up here, that the limit will exist if, and only if, the left side and the right side match. Well, they don't. So this is a does not exist because the limit of f of x as x approaches 0 from the left does not equal the limit of f of x as x approaches 0 from the right. Because the left and the right-sided limits don't agree, the full limit does not exist. Now, did we draw f of x? No. Were we given a graph of f of x? No. But by looking at the specific pieces that the limit is referring to, we can use direct substitution as a way to find the limit. And then we get to letter D. Letter D is not asking for a limit. Letter D is asking for the y value. the function value, specifically the function value at 0. So am I going to use the top part or am I going to use the bottom part? Where would x equal 0? Well, if I look at my equation, it's not the top part because that's for x's that are less than 0. It is the bottom part because it's where x's are greater than or equal to 0, and I have an equal to 0. So if I substitute 0 in for that, it's going to give me the y value of this graph at x equals 0. Mr. Barrientos, isn't that what we did on part B? It is. We used direct substitution by plugging in 0 to figure out the limit from the right. And when we did part D, we did substitution of 0 into the part that we were looking at that included the x value that we were looking at, which was 1 as well. That's video number 1. We can evaluate limits and function values, which we did in pre-cal, of piecewise functions by looking at the particular piece and using direct substitution.